All right, let's dive into a technology that doesn't just upgrade our computers, it completely rewrites the rulebook on what's even possible. We're talking about quantum computing, a field that runs on the truly mind-bending laws of the universe itself.
So, to get a feel for this, let's just start with a quick analogy, a game of chess. Your standard computer, a classical computer, it looks at every possible move, but it has to do it one by one by one. It's powerful, for sure, but it's sequential. A quantum computer, it looks at all the possible moves at the exact same time, and that's the whole game. It's not just about being faster, it's about a kind of parallelism that is just on a completely different level.
So how in the world is that even possible? Well, to really get it, we've got to look at the very building blocks of this new reality. And trust me, they are fundamentally different from anything you'd find inside your phone or your laptop.
Okay, so every computer you've ever used runs on bits. And a bit is super simple, right? It's either a 0 or a 1. That's it. Think of it like a light switch. It's either on or it's off. There is no in between. Quantum computers, on the other hand, use something called a qubit. Now, a qubit can be a 0, it can be a 1, or, and this is the part where your brain has to stretch a little, it can be both at the exact same time. This both state is where all the magic really begins. This wild property is called superposition, and probably the best way to wrap your head around it is to picture a spinning coin. While it's up there, flipping through the air, is it heads or is it tails? Well, in a way, it's kind of both, right? It only becomes one or the other when it finally lands, or in quantum language, when you measure it. A single qubit in superposition holds so much more information than a simple on or off bit. But honestly, it gets even weirder. When you bring qubits together, they can do something called entanglement. This is when two or more become linked in this really spooky, special way. Whatever happens to one of them, instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy. So when you link up qubits like this, their computing power doesn't just add up, it grows exponentially. So you combine this idea of superposition with this spooky action at a distance of entanglement, and what you get is a machine with the potential to solve problems that are, for us right now, literally impossible. So let's take a look at what this kind of unprecedented power could actually mean for our world. So how does this power really scale up? Well, check this out. A regular computer making, say, 10 calculations does them one after another. But a 10-qubit quantum computer can perform 2 to the power of 10. That's 1,024 calculations all at the same time. And here's the real kicker. If you add just one more qubit, just one, that power doubles. That exponential growth is why people call this a revolution. And what could you do with that kind of power? Well, here's the application that always grabs the headlines. All of our modern digital security, online banking, secure messages, it all relies on encryption that's just too hard for normal computers to break. For instance, cracking a common type would take the best supercomputer we have today about 1 billion years. A powerful enough quantum computer, it could do it in less than a minute. Just think about that, 1 billion years versus a coffee break. But this power goes way, way beyond just breaking codes. The real promise here is in solving some of humanity's biggest, thorniest problems. Just imagine simulating molecules to create new medicines, cutting down drug discovery from a decade to just a few months, designing brand new materials atom by atom, building AI that can chew through data sets that would completely choke today's supercomputers, or optimizing our energy grids and financial markets with a complexity we can't even fathom right now. I mean, this is the world that quantum computing could unlock. It's an absolutely incredible vision, right? But that vision is still a very long way off. And now we have to pivot to a pretty sobering reality check, because the hurdles between here and there are, and I mean this, absolutely monumental. A few years ago, the whole field was electrified by this big announcement. Google said they had achieved something called quantum supremacy. Basically, they performed a very specific, very niche calculation that they claimed would be impossible for any classical computer to do. It really felt like a massive breakthrough moment. But then, almost immediately, came the counter-argument. IBM, one of their biggest competitors, pushed back hard. They argued that Google's estimate of 10,000 years was just wrong, and that with the right programming, their own classical supercomputer could solve the exact same problem in just 2.5 days. And this whole debate just shows you how contested and complicated this field still is. So the critical question is, why is this so hard? Well, the single greatest enemy of quantum computing is something called decoherence. Remember those super delicate quantum states like superposition? They are unbelievably fragile. I mean, it's like trying to do math on the surface of a soap bubble. The tiniest vibration, a tiny change in temperature, any little interaction with the outside world can knock a qubit out of its state, and poof, the entire calculation is ruined. And decoherence is really just the tip of the iceberg. The errors it causes are incredibly hard to fix. Then, as you try to scale up and add more qubits, the whole system just gets exponentially more fragile and prone to errors. And you have to manage all of this inside these multi-million-dollar machines, often kept colder than deep space, just to keep that quantum state stable for a tiny fraction of a second. So all of this leads us to a really blunt but really honest assessment from the journal Nature back in 2023. When they asked what today's quantum computers are actually useful for, like for a real-world task that they can do better than a classical computer, the answer was absolutely nothing. For now, they're incredible, fascinating, but still highly experimental tools for researchers. So you've got this incredible, world-changing promise on one side and these monumental, maybe impossible problems on the other. Where does that leave us? What does our quantum future actually look like as we try to navigate this totally unwritten path? Well, it helps to see this whole thing as a very long journey. The idea was first floated way back in the 1980s. A key algorithm that showed what was possible came out in 1994. Then that supremacy debate in 2019 kicked everything into high gear. Right now, we are in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. The machines are real, but they're still small, they're very prone to errors, they're noisy, and they're not changing the world yet. But the revolution is definitely underway. And it is so important to frame this correctly in our minds. We aren't just building a faster horse here. This is like the invention of the automobile. It's a fundamental, paradigm-shifting new way to process information. It's potentially as big a deal as the spinning jenny was at the dawn of the Industrial Revolution, kicking off a whole new era of what machines are capable of. You know, in the end, it kind of brings to mind what Isaac Newton once said, that he felt like a boy playing on the seashore, finding a prettier shell here and there, while this great ocean of truth lay completely undiscovered before him. We think we know what quantum computers can do, break codes, design drugs, but the real truth is we have no idea what we're actually going to find when we can finally explore that vast, undiscovered ocean. And that is both the biggest challenge and the greatest promise of all.